going over Sipser's Exercise 4.2 in the textbook. The problem is, consider the problem of determining whether a DFA and a regular expression are equivalent, and express this problem as a language and show that it is decidable. So let's start by creating a language, and we will call that A, and we will express it like this. R and B. R is a regular expression, and B is an implementation of R as a DFA. All right, so now that we have the language, we need a way to decide A. And we'll do that by using a Turing machine. So I'll create Turing machine M1. Sorry about the mistakes. So we'll start this by converting R to an equivalent NFA using Sipser's theorem 1.54. And theorem 1.54 states a language is regular if some regular expression describes it. So for example, if R equals A, just A, and A is a subset of sigma, then the language of R equals A. And if we were to have an NFA that describes it, it would look something like this. Let me just move that. Right. So now we need to convert the NFA to a DFA using Sipser's theorem 1.39, which states every NFA has an equivalent DFA. And in this case, we're going to call the new DFA DFA A. And I won't go through converting the NFA. We can just assume that there is a DFA for the NFA. So we have two DFAs. Now we need to see if they're equivalent. So to do this, we'll need another Turing machine. So we're going to create Turing machine F. And we will use this from EQ DFA on input A, B, where A and B are DFAs. And if you recall, we have already defined B as a DFA, and we already created A by assuming it is a DFA that's equivalent to the NFA we created from R. So EQ DFA equals A, B. A and B are DFAs, and which means the language of A equals the language of B. And oh, sorry, I forgot to mention this is in Sipser's theorem 4.5. Sorry. All right. So we're going to create a DFA called C. And the language of C is equal to this expression here. So basically it's saying the complement of A intersected with the language of, the complement of the language of A intersected with the language of B, or union, or the language of A intersected with the complement of language of B is equal to C. And the theorem states that if C is equal to the empty set, then we accept. Otherwise, we reject. And if Turing machine F accepts, M1 accepts. If F rejects, then M1 rejects. And that's basically how to walk through that. You can see that C will always be the empty set if languages A and B were equivalent. If there were anything else, then C would not be the empty set. And I have a little illustration to show how that works. You can see here we had an input language A, and from that we built DFA A, and we already had input DFA B already defined up here. We had Turing machine F use equivalence testing to see if they were equal. And if they were equal, we accepted. If they weren't equal, then we rejected. And that is how to solve problem exercise 4.2 in Sipser. Thanks.